hit return, and we're in the analysis again, and we go to the load steps panel, which is right here. So we're going to create a new one, and the name, we're going to call this one break. And click enter. And then on the type, we want to make sure this is linear static, which is usually the default. And then we check the box next to SPC. Now what we're doing here is we're making a case. We're saying that there's a case of loads and there's going to be a constraint, these SPCs, and it says, okay, which load collector contains the SPCs? So I click on this and I select SPC. So now it says, okay, the first number 1, the ID number 1 of the load collector contains SPCs, and what loads do you want in here? And so we click on here, and since we're doing break, we're going to click on break. So in the break load case, there's going to be SPCs, which are 1, which are the SPC, and the loads will come from the break load collector. And I think that's it. Yep, and we just click create, and now we have a new load step called break, which takes into account break, load collector, and the SPC. Now we're going to make 2 more for the other 2. Corner, the SPC, we want it to still be number 1, and the load in this case we're going to make corner, number 3. Still linear static.
What does the 1 next to SPC refer to?
It refers to the ID. The ID of the SPC load collector is 1, so that's why it's 1. Load in this one is 3. Oh, whoops.
And those SPC load collectors, those are the ones inside the, basically inside the axles, or the.
Oh, the ones in here, like the triangles.
Yeah.
These numbers refer to the number of degrees of freedom at that constraint.
Right, but the SPC, that load collector is that node that you've got there, and the right.
Yeah, those constraints.
Okay.
Right.
Okay, that's what.
So corner. So I'm going to click create, and then on this we're going to make one more for the pothole. And SPC is already set to 1, which is the one we know we want. And we're going to change the load to pothole number 4. Linear static, create. Okay, we have those 3 load steps now. Or load steps or load cases. And okay, we'll click return to go back to the analysis page. Okay, now we need to make a design variable. So we go to analysis, optimization. We'll bring up another panel here. And we're going to make a topology optimization. That's what we're going for. So on the create, we want to make sure we're on create, and desvar, so we're going to call this one design prop.
Good question.
Mm-hmm.
What is a load step?
What is a load step?
The objects are making load steps. What are those for?
As far as I understand it, what we're doing is you have your loads in the load collectors, and you have your load steps, which are basically different cases. So we're looking at case 1, what happens if I only have the break, the loads from break, this load and the SPC, what happens to in the simulation? And then in case number 2, for the corner, what happens if we have the corner loads and the same SPC? And then case number 3, what happens if we have the pothole? And then I think it'll do one also with everything together.
It's a way of connecting the loads that we added with the SPCs.
Yes, it's kind of setting up the case, the condition. In condition number 1, in this first simulation, this is what's going to happen. In this simulation, this is what's going to happen. Good question, though. And to be honest, I don't fully comprehend everything that's going on here. So I know how to set it up, but it's taken me a while to still try to get around why they have everything here. It's not super simple and simple. Okay, so where are we? Okay, so desvar. By the way, I'm on step 7 if anyone's following along in the tutorial, if you want to follow along. So I'm on design property, and then properties, which one I want to select, and I want to be design prop. So I click select, and the type, we want to make sure that's P solid, and we click create. So here it says, it explains, it says a topology design space definition design prop has been created. All elements organized in this design property collector are now included in the design space. So we made a property determining what will be the design space and what will be the non-design space, and linked that to the actual components of which. But in this case, we actually made a variable saying this property will now be considered design space. Everything in this place, in this property. So that's what that did, basically. So we click return to go back to the optimization, and now we want to create some responses. So we're still right here in analysis optimization. We go to responses, and response we enter vol, because we want to create a volume response. And response type, we want to make this one a volume response. And regional, we want to make sure this is on total, and then we click create. So now, and then let's see, and it has us make another one called disp1. And this one will be not a response type of volume, but a response type of static displacement. And then now it says, okay, so this response will be at what nodes? What nodes do you not want to? You want to constrain the displacement. And so we click on nodes, and by ID, and 2699 is what we want to enter, which is that same node there. And we want to make sure that we click total displacement in this case. So it says this is the vector sum of the x, y, and z translation. So we're according to the simulation we have set up, this is constrained, this is constrained, this is constrained, but the forces will still make this thing bend and move. And so we're putting some kind of a response that will limit how much that's going to be able to move. And it'll take that into account. All right, we need to click create, and now we have that disp1 response. So we go back to the optimization, and we need to define an objective. So if we go to objective, and we want to minimize, and the response we want to minimize is volume. So what we're doing here, create, is we're telling this is the objective of the optimization is to minimize the volume in this space. Does that make sense? That's the objective it's going to go for. So now we click return, and now we go to deconstraints in the optimization panel, and we're going to make a constraint called constr1, and we want to select upper bound, and the value we want to set in there is 0.05, and the response is disp1, and the load steps is break. Select and create. Okay, so what did we just do here? We just made a constraint. So when you make responses, you have to set one of these responses, you have to constrain all of the responses except for one. So you have like different possibilities of what could happen, I guess, is one way to describe the responses. And you constrain all of those except for one, and that last one you let the computer then optimize. It's the one variable that it has. The other ones are all constrained, so it's only one variable it has to deal with. So in this case, we just constrained the say what?
Displacement of the node force.
Yes, we've just the displacement 1 of the load step break. We said the upper bound, the most that thing can displace will be 0.05. And so we're going to do a similar thing. We're going to make constraint 2, and we're going to. It's still on. Here's where the editing comes in. In this part, the tutorial is wrong in step 10. So the PDF on the website describes it a little better because it's confusing because they say to click in responses when you should actually click in load steps. So just so you know, we're gonna leave response as disp1, and we're gonna select the load step. First of all, we're gonna unselect them all by clicking this button, and then we're gonna select corner. Select. So in this case, for constraint 2, we're constraining the corner load step to displacement due to the corner to only displace 0.05. Or actually, this one we want it to be 0.02. And click create. So there's constraint 2. And similarly with constraint 3, the upper bound for that one is 0.04, and the response is disp1, and we want that one to be pothole. And we click create. So now we have those 3 constraints.
That upper bound constraint of 0.04, is that in any direction?
I believe so, because displacement is is in all directions. So we could also, in other ones, I've set up optimizations before where you have two different responses. You have volume, or like volume fraction, and then you have the compliance, weighted compliance. So compliance meaning how much can this thing, how rigid is it? It's the opposite of how rigid it is. And then you have the volume of how much volume is there. So in that case, we constrained the volume to be 0.15 or something, or 0.3. So only give it 30%. Basically, we're telling it you can only keep 30% of the volume, but maximize the compliance, or sorry, minimize compliance, which will then maximize the rigidity. Does that make sense? We're basically telling it make the most rigid structure you possibly can, given only 30% of the material. So that's the relationship between responses and constraints. So the constraint would, in that case, would be on the volume, and then the objective would be on the weighted compliance. How compliant can this thing be? Okay, so now, after all that, we're ready to run the optimization. So back in the main panels page, if we go to Analysis, and then you click OptiStruct. Now, if this button's not here, you could probably do everything we did if you're in the just default user profile. But if you don't have the OptiStruct button down there, it means you're not in this correct user profile. So just go to Preferences, User Profiles, and so we click on OptiStruct, and it brings up this menu. So it's going to create a file, a .fem file, and it by default puts it in whatever folder that part is. So I think I'll just do that same thing. In fact, sometimes I even create a new folder called Results, and I'll save it in there. And then we want to export options. It says to do to all, and then run optimizations, run options. In this case, we're just going to run a check first. And all the check will do is it will just check everything to make sure that we've set it up correctly and to make sure it will run. And if it's not ready to run, it'll throw us an error. So when we're ready to go, we just click OptiStruct, and then it'll bring up this menu here. So this shouldn't take very long at all. And I don't know what those errors are about, but I think it's all right because it's still working. And if it once it's done, it'll say yes, it's checked and everything looks okay. Or if there's an error, if you miss something, sometimes it'll throw an error and say this is wrong with it or whatever. And then once we do that, I'll just click on this after we're done. If you change the run options to optimization, then it will actually run the optimization. It'll still run this check beforehand, but it will then, once given, if the check runs successfully, then it'll just run the optimization. So someone asked on Wednesday, what's the benefit of running a check first? And the benefits of that are if you want to run this simulation on a different machine that's much faster, then you can run a check. You can get everything set up and just keep running checks. Or once you run a successful check, then you know that your program, it's ready to go. And then you can just save your file and open up on the other computer and run it. So we would suggest doing that on Linux boxes. This optimization will probably take about 7 minutes to run on Windows, which is actually ridiculously long for this simple optimization. But on the Linux boxes, when I did this earlier this week, it took over 7 minutes to run on a Windows machine. But when I just saved the file and opened it up on a Linux box and ran the same thing, it ran in a minute. And so we would suggest for this class, you don't want to, because you're going to be running a lot longer optimization problems that'll take half an hour to solve. So the best thing to do would be to, there's not enough Linux boxes for everyone to be on there at the same time working on this. So we would suggest doing all of your HyperWorks, HyperMesh setup and optimization setup on a Windows machine. And when you're ready to run the optimization, save your file, log into a Linux box, open your file up, and then run it there because it'll go a lot faster. So this will eventually check. And then when you're done with the check, and the optimization will bring up a similar prompt, command window like this, and it'll just sit there with the blinking cursor, which means it's working for a long time. And so once it's done, it'll give you a success. It'll say, "Hey, this finished," and whatever. And so then, if it's done.